Right, now we can move to the next one. As we can see from the flow of the question, that this is another year 12 special semester question that is designed for our common summer topic again. Well, the main difference between question 6, like the one we did before, and question 7 is that, well, first of all, this is a pretty long question, as we can see now. And also this involves both Cartesian form and the polar form of common number as a whole. So in terms of complexity, that this question is actually a lot harder than our question 6. It's just simply because for those questions involve the polar form that can be easily designed to be incorporated with some other learning areas, like with polynomials, with geometry, trigonometry, and with vectors. So this is important question type for both VCE and the SACE, even though this is actually a past SACE exam question, but also important for the VCE students. Alright, now we can start. Question 7. Alright, we first need to write root 2 take root 2i in the polar form r c theta. So basically we need to find r and theta. So this is a very simple part that many of you have practiced a lot. Okay, so we can let common number w be root 2 take root 2i. R equals to modulus of w, like magnitude. So w modulus, that equals to the square root of a squared plus b squared. So square root of 2 plus 2 is 2. And theta represents the direction of common number w. So we can use our rectangle triangle principle of the tan inverse of the opposite over adjacent. So b on a, negative 1. Negative root 2 over root 2 is negative 1. Alright, can anyone tell me the answer for tan inverse negative 1 straight away? The answer is negative pi on 4. But many of you may say, Mr. Pan, I have learned this part of knowledge in my year 11, now I cannot forget. Can I just simply type this one, tan inverse negative 1 in my calculator straight away? Well, you can if you allowed, but just be careful. Sometimes it may show in a different direction, like different angles from your calculator. It may give you, like in this question, it may give you 3 pi on 4, or even 7 pi on 4, which is very unlikely. Why the 3 pi on 4 is not right? Because we need to respect the direction of the common number w, like the direction of the vector w. So this shows in the fourth quadrant, root 2 take root 2i. However, 3 pi on 4 it points in the second quadrant, so this is not right. Basically, as we all know, the 3 pi on 4 is just like a pi unit added based on negative pi on 4. Because the tangent function is a periodic function with a period of pi. So, even though tan 3 pi on 4 equals negative 1, this is unfortunately not the proper direction that we are looking for. Alright, so 7 pi on 4 and negative pi on 4, even though it shows in the same direction, we need to be careful for the domain of the theta. So theta is the argument of our common number. In this question, theta is arc of w. The argument, by definition, argument arc w. So by definition, arguments lie between negative pi and pi. So therefore, 7 pi on 4 lies outside of the range of the domain, so this is not right. So the answer for w, when we convert the Cartesian form in the polar form, that should be 2 says negative pi on 4. Yep, there's no doubt. The answer should be negative pi on 4. Alright, so question AI, we finished. II is hence, so next part of question A, hence we need to find root 2 take root 2i power 4. So root 2 take root 2i to the power of 4. Have you remember, we have discussed this a lot before. Whenever we deal with a higher order, higher power for a Cartesian form, we first need to change this one to the polar form so that we can apply the Fermat theorem, right? So we have done that in part A. That's why the question says, hence find the answer of power of 4. So we can use our finding, or previous finding. That equals what? 2 says negative pi on 4, power of 4. Okay? Alright, so now we can use the Fermat theorem. So 2 to the power of 4 is 16, and says negative pi on 4, like n theta, n times that theta, right? So negative pi on 4 times that 4 is negative pi. Since negative pi is a real number, isn't it? Just -1, because this is the value on the negative side of the real axis on the odd and day one. So -1 times 16 is -16. Alright, so basically root 2 take root 2I power 4 is real number, is pure real numbers of -16. And question B, here. Question B, solve z to the power 4 equals to -16 and then write all your answers in polar form. Okay, z to the power 4 equals -16, this is a real quadratic polynomial. So therefore we should expand there are 4 roots. Have you remember, as I said before, for most of the exam style questions, usually there are some inner links between sub-questions. According to our finding in A, root 2 take root 2I is one of the solutions for fourth root of -16. Therefore, the fourth root of -16 I labeled Z1, one solution must be root 2 take root 2I. The question wanted to write in polar form, so you just write in polar form. So 2 says -pi on 4. And as we all know, for real polynomials, imaginary root never just comes by itself like this. It always comes in a pair of conjugates. So the conjugate of Z1 is root 2 plus root 2I. So we can write in the polar form must be 2 says pi on 4. So now we find a pair of conjugate roots for this real quadratic polynomial. The question after this is how to find the other two roots, or possibly the other, another pair of conjugates. Remember, when we solve for nth root equation, right? When we solve for nth root equation, the nth distinct solutions will be equally spaced around the circle with the center 0, 0. So, like the nth distinct solution will be equally spaced. That means what? The angle we can see between Z1 and Z4 is pi on 2. Therefore, the angle between Z3 and 4 must be pi on 2, because the full angle adds equal to 2 pi. So therefore, Z3 must be 2 says 3 pi on 4. And Z4 must be 2 says the conjugate of this. This is another pair of conjugates, similar to Z1, Z2, must be -3 pi on 4. Can we write this as 5 pi on 4 instead? Because they both show in the same direction. Well, when we solve for nth root equation, we can either use the system, like use the domain from 0 to 2 pi, or from -pi to pi. Okay, so but we have to keep it consistent, right? We keep it consistent. For Z1 we write -pi on 4, so therefore they fall into write -3 pi on 4 as well. Okay. Alright, so now we move to question C. Question C. Question C, we now to show the division of two polynomial expressions that equal to z power 4 plus 16. And be careful, this question has only one mark. So what does this mean? Instead of using long division, right? Or normal way to show it, we can use multiplication. So because we can easily show z power 3 plus 1 times by z power 4 plus 16 that equals to z power 7 polynomial expression, right? Just by using expansion, so very, very simple. That's the question C. Question D. Based on, like, according to the answer or findings for B and C, according to our previous findings, we need to solve the power 7 polynomial, right? We need to find the 7 zeros for this power 7 polynomial. Now you can see question C is actually just a hint when you solve question D, because the power 7 polynomial has been successfully factorized into two polynomials, like one is quadratic and cubic. So instead of finding this 7 zeros directly, we can just find the 0 of this quadratic and the 0 of this cubic. For this one, we have predicted from it, like there are 4 zeros, 1, 2, 3, 4, based on the answer for B. We now just need to find the all 3 zeros for this cubic real polynomial. So we let z equals 3 plus 1 equals to 0. So now my question is, how can I find the 3 zeros for this real cubic polynomial? Well, we can possibly guess it. One of the solutions must be -1, isn't it? Because -1 equals 3 plus 1 must be 0. So I can easily say z1 equals to -1. But how can I find z2 and z3? Well, we always need to keep in mind that whenever we solve the nth root questions, the nth distinct solutions, for this question there are 3 solutions, right? So the nth distinct solutions will be equally spaced around the circle. So one, I probably just draw on the outline diagram. That might be easier for you to understand. So -1, 1, 0 is real imaginary. So 1, 0 is -1 here. Because question one you to write in polar form, so you better write as it says pi. Right? So in this outline diagram, right, 1, 0 is -1, and the other two roots must be 120 degrees apart, right? Because in all that will be 360. Because the 3 distinct solutions will be equally spaced around the circle. So if this is Z1, then Z2, Z3 must be here. And 120 here, 120 here. So this is 60, so pi on 3. So this will be Z3. The direction for Z3 must be -pi on 3. Therefore, Z2 we can write in polar form as well. By the way, the modules are the same, right? 1 unit, 1 unit, 1 unit. The modules keep the same, but the angle shows different directions, right? Shows 3 different directions. So pi on 3, and this is -pi on 3. All right. Some students may say, well, Mr. Pan, if, for example, if I have no such prior knowledge on finding these two roots, like according to the like this technique I have used in here, like the nth root of distinct solutions will be equally spaced. If I have no such prior knowledge for this technique, how can we solve this cubic polynomial? Well, you can just solve this as normal way, isn't it? We can just use the Fermat's theorem to solve it, right? So z equals 3 plus 1 equals to 0, therefore z equals 3 equals -1. We first need to convert -1 into a polar form, so that be very simple, just equals to 6 pi. And as we all know, there are 3 roots, right? There are 3 roots, and the period for 6 is 2 pi. So therefore, z equals to 6 pi plus k loss of 2 pi, isn't it? Or k belongs to the integer, like 1, 2, 3, -1, -2, -3. So k loss 2 pi, so 2k pi power of 1 over 3. Now we can use the Fermat's theorem, very simple. Therefore, z equals to the modulus of 1, so 1 to the power of 1 over 3 is still 1, and n theta, so 6 pi over 3 plus 2k pi over 3. That's it, and then you can write k belong to integer, like 0, 1, 2, 3, 91, 92, 93, and you can discuss the different value of k, and you can find the answer, pretty much just like these 3 answers, right? These 3 roots. So this method is called the complex number method. We use we first need to convert Cartesian to polar, and then we can use the Fermat's theorem. Instead of using this way, we can also use the polynomial method, right? If you have learned the polynomial. So method 3, z to the 3 plus 1 equals to 0, right? If we can factorize this as this one of the roots we know, because I remember like my question was, if I can guess one root, how to find the other 2 roots? If I have no such prior knowledge on this technique, we can use method 2 or this method 3. So one root is -1, therefore the factor is z plus 1 times by what? there's a linear, like to get a cubic polynomial, we can factor this cubic into linear times a quadratic, isn't it? So z squared, z times z squared equals 0, 3, and 1 times by 1 equals to 1, the constant. So constant must be 1. And how can I find the middle term? I just say AZ. We just need to find the coefficient for z. Well, very simple. We can use the technique. It's called equating the coefficients for both sides. So we have used the z equals 3 to define z squared. We have used 1 to define 1. So I have to use. We now need to use the middle terms. Yeah. So the coefficient for this middle terms must be 0. So it doesn't matter to use which one. So say if I use the z squared term, so that will be 0 z squared. You can use the z term as well. Doesn't matter, up to you. So left hand side we have 0 times by z squared, and to the other side, to get z squared term, and we can use z times by az, so it will be az squared, or 1 times by z squared, just the 1z squared, and this squared all cancelled. So therefore a equals what? Just 91. 0 equals to a plus 1, so a equals 91. Yep, so very simple.